Thank you all for coming. I'm Scott Loftin, and today I'm going to be talking about some work I've been doing over the past semester with Carl Schussler, supervised by Dinesh Manocha, in the Gamma group on acoustic material recognition. So I'm going to be scrolling this. Doesn't look quite as good. So brief overview of what I'm going to be talking about. I'm going to start out with some background and motivation for the problem, namely sound propagation and sound in virtual environments. Then I'm going to talk about acoustic materials, which is the focus of the project, and finally on classification, which is where I come in. Then I'm going to present some results, just what the actual classifications look like, and then finally discuss some challenges, future directions, ongoing work, things like that. So sound for virtual environments. So when we think of computer graphics, we usually think of visual rendering. So the idea there is that you're given some description of a scene, and you want to generate an image of that scene based on that. Sound is not so sophisticated. So with sound, you're usually dealing with either raw recordings that are played back in the scene, or they'll do some volume modulation to give you the illusion that a sound source is further away or closer. They'll do stereo mixing to give you the illusion that it's closer to one side or the other. But what they generally don't do is what's called sound propagation for spatial audio, which is how you actually get parts of the scene to interact with the sound as it propagates in, and then have that be reflected in what the user actually hears. So when I speak in this room, it's not just a sound source. It actually goes out, reflects off the back wall, reflects off the floor, and interacts with different materials in the rooms in different ways to give listeners the impression that they're standing in this space versus outside or in a smaller room or something like that. So I'll give you a brief picture of what that looks like. So again, the idea behind this is sound propagation. We're using geometric sound propagation, which was mentioned in one of the earlier presentations. And the idea behind that is that at high frequencies, sound can be approximated by array, like with ray tracing for light. And so given a model of the scene with those acoustic parameters and a set of source and listener locations, in this case, the sources are in red and the listener is in blue, you can propagate out from those sources, have it interact with materials in the scene, and then gather them back at the listener location. And you can simulate how a sound source played in that scene would sound like in that environment, in that virtual scene. So what do we need to do this? Well, two things. First thing we need is a model. So we need a geometric model of the scene. This is very well studied in computer vision. It's one of kind of the core problems in computer vision. And there's a lot of really good work on using particular depth cameras like this Connect V2 to generate high quality meshes of a room by just waving it around or using fusing results from multiple Connect cameras. And we actually ended up using some very excellent captures done by members of Dr. Fuchs's group of some offices here in Citterson for our simulations. You also need acoustic materials. So as I mentioned before, different materials in the scene are going to interact with sound in different ways. So something like carpet or acoustic foam is going to be a lot more absorptive. So sound's going to hit it. It's not going to reflect off a whole lot. Versus a material like brick, stone, tile. Those are going to be a lot more reflective, and you're going to get a lot more reverberation where the sound goes, hits it, and then reaches the user again a second time, and then repeats. So you get this kind of echoey effect. And the question we wanted to address with this project is, can you do this automatically? So there's a lot of work that's been done on capturing geometry, but the acoustic material labeling is usually done by hand, and that's very time-consuming because you need an expert, somebody who knows what different sound materials look like and where they would go in a scene, to actually either label or just build the scene from materials that have already been classified with an acoustic set of acoustic parameters. So real quick, I'm going to play a video of what that sounds like, just to give you an idea of how the materials affect. All right, let's see if I have the right. Okay, I think I might just refresh it.
Just click on you do the material one first.
Okay. Oh, there we go.
A key part of generating quality of sound is determining the acoustic material properties. The acoustic materials that are present in the scene have a strong effect on the resulting sound. This is a small rectangular room with a floor made of marble tile, brick walls, and plaster ceiling. If the walls of the room are changed to gypsum board and the floor is changed to wood, the reverberation time decreases and there are less low frequencies. If the floor is changed to carpet, the reverberation time is reduced further due to the high absorption coefficient of the carpet material.
So thanks to Carl for letting me steal this video. So yeah, material is important for sound, and we'd like to have some way to do that automatically. So the basis for our classification were neural networks for vision, specifically convolutional neural nets, which have gotten a whole lot of press and were the subject of, I think, a couple of other talks today. The idea behind that is that you've got some architecture. In our case, we use GoogleNet, which is a very successful neural net for classifying images. And They propagate lots and lots of training samples, usually tens of thousands, through the network, evaluated against some loss function, and then back propagate through the network in the opposite direction to update the weights. And this way, the network actually learns these underlying features. So if you look at the far left, those are low-level features, and then you'll have layer after layer that you have activation functions that cut off, that basically apply a threshold so that you only want to have them turn on when you see a certain feature to a certain degree, and then you have subsequent layers that actually build, actually learn features on top of those initial features. So a very powerful architecture, very successful in the last few years for a lot of image recognition and segmentation tasks. And the issue here, though, is that you need lots and lots of data. So that's fairly straightforward for things like classifying objects, but for materials, not so much. So we use the materials and context database and the model that they released last year, which included about 3 million point classifications for 23 different material categories. And you'll notice that not all of these are acoustically relevant. So you've got things like skin, hair, food, which don't really affect acoustics too much because the areas that they're going to be covering are so small, and you're not likely to see them in most scenes. But most of these, about 18 or so, were actually relevant, so we were able to use those for our simulations. And like I said, they fine-tuned GoogleNet to classify these, and now I'm going to show what those look like. So these are some results from our classification pipeline based on Mink for one of the rooms in Citizen. This is SN348, which is an office. So you've got carpet, you've got paint on the back wall, you've got a world map, which is paper on the top left. And so these are heat maps, probability heat maps, which are the lighter the color, the more likely it thinks that material is there. So it's got a confidence vector that's going to spit out for all 23 categories. We take one of those values, and then we map all those values to a single image for that category to give you kind of a picture of where different things are located in the scene. So in the top right, you've got painted, and you can kind of see the outline of that world map on the top left. You can see the silhouette of the desk. So that worked okay. On the bottom right, you've got wood. It's picking up the wooden desk and chair. Let's look at a couple of other categories for tile. Less obvious because the tile is kind of dark, and it's also not immediately apparent to, even if a human was trying to label this would be difficult. But you can kind of see the outline of that light fixture at the top. The bottom right, you've got paper, which is picking up that paper bag. More categories, plastic and wood. Wood, it's picking up a wooden coat rack right in the middle. And let's see, metal was another category that I was pretty surprised it picked up. If you look at the top left, there's that metal AC fixture. And it doesn't pick it up too well, but it does seem to notice that there is something metal in the top left of the scene. So those are results for Connect 640 by 480 RGB images. Resolution matters. So these are some results for much higher resolution images. This is an image from a company called House, which does photography for real estate, and was actually one of the images they trained the network on. So they took patches from this image and used that to actually do the training. And you'll see that when we run the network on this image, you get better results. So you can actually see in the top right, it distinguishes between wood and paper on the bookshelf. You can see on the bottom right, that's fabric, which is it's picking up kind of the two chairs in the middle. On the bottom left, it's paint. So it's picking up not only the paint on the walls, but also the paint on the wood on the bookshelf. And then on the top left, as you may be able to guess, is brick. So given high quality images, it can perform very well, but one of the limitations we ran up against was the resolution of Connect images that were used to actually create the room reconstructions. So Carl took these, projected them into the room, and so what you'll see at the top row are the Connect room reconstructions from Dr. Fuchs's group. In the middle are the classification results that had been projected into the room from their original camera poses to basically paint the scene with material categories. And then at the bottom, we have some ground truth. So these were actually generated by Carl just went through and painted these with what he thought the materials were. So you can kind of compare the second and third rows, and you'll see that they're not great in some instances, especially on the left, but it does seem to be pretty good at picking up things like fabric. So the couches in SN229 and SN251 showed up pretty clearly. The carpet, it seemed to pick up. Paint, it was very good at picking up. And yeah, so that's what we had for classification.
So what's different about the ones on the left?
On the left, oh, it's a lower quality classification. It doesn't look as good. It was the same approach though. So yeah, so that's what we had for a classification. And the question is this good enough? Can we just do this? Can we take images of the room, classify them, project them in, and then do the sound simulation and have that work? Turns out not really. So that's where we gave up. No, actually, so we actually employed an optimization pipeline, but the reasons it didn't really work by itself is that, well, first of all, there's only about 18 categories we're able to use, which is, again, that's because we chose the Mink data set. It's very difficult to get data sets for materials because humans aren't good at identifying them, and training neural networks that can pick up based on just a patch of material that can actually classify it at its center is very difficult. So it takes a lot of, they have a very complicated labeling pipeline to get that data that they can actually use to train it. And there's also things like you have limitations from within individual categories. There's a lot of variation. So there's different kinds of carpet, different kinds of wood, different kinds of stone, and also the way that rooms are constructed are going to affect the results. So the way we get around that is with an optimization pipeline. So this was Carl's work. The idea here is that since we limited ourselves to actual scenes that we have access to here in Citizen, we can take measurements of the acoustics in those scenes. In particular, we can measure what's called the RT60, or the reverberation time, over for 60 decibels. And the idea behind that is you measure how long it takes based on you generate a sounds in that space, and then you have a speaker, and you measure how long it takes for the sound to drop below 60 decibels in that room. And then based on that, you can get an impulse response, which is a function that you can apply to sounds. To basically, you can do an operation with that function and a pre-existing sound source, and then generate how it would sound in that scene. And so what you can do is you can compare the two. You can compare the sound we get from the 3D model and the virtual sound rendering, with the measurements from the actual scene, and then you can adjust the materials accordingly. So it's usually about 7 or 8 iterations, and the idea is that you compare the two, and then you can actually scale the absorption parameters of all of the materials in the scene at once to better match the acoustics. So I'm going to play a video of what that looks like, or sounds like, rather. Optimization. Yes, here we go.
This is the measured response. This is a simulated room impulse response with visually classified materials. This is the simulated room impulse response with optimized absorption coefficients. This is the measured room impulse response. This is the measured room impulse response. This is a simulated room impulse response with visually classified materials. This is the simulated room impulse response with optimized absorption coefficients. This is the measured room impulse response.
So the takeaway from that is you heard at the beginning the measured response, and then immediately after the classification response. So that's the result from just the visual classification, and it wasn't very good. But what it's useful for is initializing this optimization step so that we can get a much better final result if we employ the actual measurements from the actual scene to optimize. So yeah, there were a lot of issues with this. Again, a big one was finding good models. They're pretty hard to come by because they're hard to make. We got 4 very good ones from Dr. Fuchs's group, but finding models that have the original depth images, the original RGB images, the camera poses, there just aren't a whole lot of data sets like that. Patch size and image resolution. I mentioned before, if you have higher resolution images, you're going to get a better result. And since we're using the Connect V1 images, which were only 640 by 480, the results that can kind of limit how good things are, especially at boundaries between categories. And it's slow. So the implementation that we used for our classification differed a whole lot from what they did in the paper, just because it was easier for us to implement it this way, which is just you take the classifier and you slide it across the image, and then you map the classifications to entries in a grid. They actually made some modifications to the network itself and made it so that it would output a single set of predictions for the entire image. So it's just one pass. It takes about a half hour, and then you have the images for the entire thing. Versus if you slide it over, you've got to do one for each grid entry. So you end up spending several hours per image, and there are hundreds of images in each data set. So I'm making some changes to hopefully speed that up. Another thing that I'm working on is manual segmentation. So figuring out that sometimes the neural net segmentation isn't good enough. It would be nice to have some quick and easy way to label entire scenes, or at least connect models with the user that doesn't require that they actually go through and just select every pixel. So there was a really cool piece of software called Semantic Paint that was released last year. And so I built that and have been playing around with that. What that does is that it lets you basically do connect fusion captures, which are it's a fairly well-cited algorithm for fusing connect images together, and you get an underlying model. And then you can actually apply a label and then watch it propagate through the scene. It propagates it to all surfaces that share a similar surface normal. So you'll notice that it'll kind of stop the classification at boundaries between surfaces, and then you can apply a new label to different parts of the scene. And yeah, so we're hoping to use this to apply sound labels to our models. And yeah, that's where I stop. Questions?
So have you considered doing something like trying to classify what an item is in an image and using that as a weight for classifying what it's made out of? For example, like an image of a vehicle. You can tell that vehicles are often made out of metal, so that would mean that that section of the has a higher weight of including metal.
Yeah, so we've looked into that. So there's actually a whole lot more that's been done on segmenting images according to objects than by materials. And so there's even there's a fair bit of work on joint segmentation. So the idea behind that is that you segment for both material and object, and then you can fuse predictions from the two to get just output final material categories. But again, the issue with that is there aren't many models that I'm aware of or data sets that fuse the two. And you also, I've looked at the results for things like Coco, and they're great at picking out, objects like a keyboard or a computer monitor. But things like back walls, it'll just say that's a wall. I mean, that's not good enough. You need to know that it's paint. You need to know that it's fabric. It's acoustic foam. And so that's definitely something we could look into. One thing you could do is you could overlay two sets of predictions and try to do it that way. But yeah, it's tricky. Anyone else? Cool.